Hello and welcome to the week 10 extra exercises walkthrough video. This is going to be our last walkthrough video, and it's also going to be a little bit different because we're focusing on some more theoretical content around different number systems that are used in computing. And the reason that this is important is because when we start to work with hardware in second year and beyond, if you choose the electrical or IoT streams, then these number systems and how they're used by the hardware become more important. So yeah, in this video, we'll be focusing on converting between different number systems. Hopefully you have enjoyed these extra exercises and enjoy the rest of this video.
It's probably going to be quite a long one, so feel free to use the chapter markings in the description to jump through to any particular exercises that you wanted to have a look at. We'll start at the start, converting binary to decimal. I'll bring up a whiteboard now. So the first question asked us to convert the number 0, 1, 1, 0, 1, 0, 0, 1 from binary to decimal. So the approach that I sort of would take to this is to draw a table. So I'll try and make this as square as possible. So in this table, we'll have kind of 3 rows. The first one is for our actual number. This one's going to be for like our place values of binary, and this one's going to be kind of combining the two. So I guess the interim result. So with binary numbers, we sort of start from 1 and we double each time in terms of the place values. So this is the bit for 1. This is the bit for 2, this is the bit for 4, this is the bit for 8, this is the bit for 16, 32 for that one, 64 here, and 128 here. So it doubles each time. So when the bit is 0, effectively that's switched off. So we don't include 128 in our math. When it's 1, it's switched on, so 64 is part of it. So I'll show you with the table, and I'll also show you how you can kind of shortcut this a little bit. So let's start with the table. I'll divide this up into, let's make that black again, into hopefully 8 relatively even segments. These are not going to be even at all, but that's okay. All right. So we have 128. Oh, actually, sorry, this is going to be our actual number. So we're going to write in our binary number here. 1 bit per section. So just ignore this last part of the table, we don't need it. So in the place value, that's where we're putting in our kind of binary number place values. So the 128, 64, 32, 16, 8, 4, 2, 1. You could work the other way around if that makes more sense to you, like starting at the smallest and doubling up. So the result section, we kind of multiply these numbers. So 0 times 128 gives us 0. That's been switched off. 1 times 64 gives us 64. 1 times 32 gives us 32. 0 times 16 gives us 0. 1 times 8 gives us 8. 0, 0, 1. So wherever there's a 1 here, wherever there's a 1 up here, we actually keep the place value. So if there's a 1 here, it's on. If it's a 0 here, then it's off. So then to calculate the actual answer, we add up all of those numbers in the result row. So we can kind of skip the zeros and just go 64 plus 32 plus 8 plus 1. That's going to give us 105 as our answer. So in other words, this binary number here is equal to 105 in decimal. So the little shortcut way to do it is just to kind of, I guess, know your place values and only add up the ones where it's a 1. So from here, if you get familiar enough with this table, you could just jump straight to 64 plus 32 plus 8 plus 1. However, I would really recommend using the table until you're feeling pretty confident with binary. So that's question A. I'll get rid of this now and write up question B. I'm just going to kind of keep the table mostly intact so that I don't have to draw all that again. and all this can go to. Cool. So question D was 1, 0, 1, 1, 0, 1, 1, 1 to decimal. So again, we can fill that out in the top of our table, 1 bit at a time. Wherever there's a 1 in the num row, we keep the place value. So 128, 0 for 64, so that's 0. 32 is on, 16 is on, 8 is off, 4 is on, 2 is on, 1 is on. So then we can go through and add up all of those numbers. 128 plus 32 plus 16 plus 4 plus 2 plus 1. And that's going to give us 183. So the answer there is 183 base 10. And then question C asked us to work out what the largest number is that could be represented using an 8-bit number. I'll just share that screen again so you can see the question. So write down the largest possible unsigned 8-bit binary number and convert it to decimal. So this question is pretty much looking at what can we do to make this as big as possible, and the answer is to turn on all of the bits. So again, I'll just sort of keep the table from before so that we don't have to go through it all again. So if all of the bits are on, that's going to be our largest number. So let's turn them all on. And probably should also erase the result here. I can keep those ones that were already on. So now we've turned on 64 and 8 as well. So our answer in this case is going to be 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. And if you add that all up, you'll get 255. So the largest number that can be represented with an 8-bit binary number is all ones, and that's equal to 255 in base 10. So that's question 1. Question 2 asks us to go back the other way. So we're going to convert decimal to binary, and there's actually 2 methods of doing this, the subtraction or the remainder method. So I'm going to show you both, and you can kind of decide which one's the most helpful for you for binary. Let's bring up that whiteboard. All right, I'll just clear this whole screen now. Okay, so the way that we do subtraction method is again using a little bit of a table. So I'll draw up a little table for this. So this table is going to have, I'll make it 4 columns, but you can cut it down to 3 columns once you're feeling confident. All right, so these columns, we have the number, we have the place value, we check if the number is greater than or equal to the place value, and then we have kind of the result bit here. So let's see how this all works. Question A was converting 171 with a base of 10 to binary. So that's the first number we put here. In terms of the place values, we're looking at all of the place values from before in descending order. So we start at the biggest, and we can write them all down now actually. So let's just do that. So we check, is 171 greater than 128? The answer in this case is yes. And because the answer is yes, the result bit is 1 there. Then on the next line here, we actually do 171 minus 128 to give us 43. And then we go, is 43 greater than or equal to 64? The answer is no, so the result bit there is 0. Then we carry 43 down to the next line, and we ask the question again, is 43 greater than or equal to 32? In this case, the answer is yes, so the result bit is a 1. And then we do 43 minus that 32 to give us 11. Then we ask the question, is 11 greater than or equal to 16? The answer is no, so we get a 0 bit there. We carry down the 11, ask the question again, is 11 greater than or equal to 8? The answer is yes. So we put a 1 there, and then we do 11 minus 8 equals 3. Is 3 greater than or equal to 4? No. So that's a 0. Carry the 3 down. Is 3 greater than or equal to 2? Yes. So that's a 1. 3 minus 2 equals 1. Is 1 greater than or equal to 1? Yes. So that's going to leave us with a 1. So then we read the answer down this way, and we end up with 1, 0, 1, 0, 1, 0, 1, 1 for that one. So we know to stop because at this point we're out of place values. So that's kind of where we end with that one. So that's the first one. We'll also do 2 more. So the next one is 203. And again, I'll kind of keep the table. I'll just erase the actual results from it. Those and get rid of those. So our next number 203, we start by asking the question, is that greater than 128? Yes, so it gets a 1 bit. So 203 minus 128 gives us 75. Is 75 greater than or equal to 64? Yes, it is. So another 1 bit. So then we do 75 minus 64, which gives us 11. Is 11 greater than 32? No, it's not. So we get a 0 there. Is 11 greater than or equal to 16? No, it's not. So we put a 0 there. Is 11 greater than or equal to 8? Yes. So that gets a 1. And then we subtract 8 away to give us 3. Is 3 greater than or equal to 4? No, it's not. So we get a 0. Carry the 3. Is 3 greater than 2? Yes. Then we do 3 minus 2. Is 1 greater than or equal to 1? Yes, it is. So the final bit is a 1. So again, we read down the page and we get a result of 1, 1, 0, 0, 1, 0, 1, 1 as our number there. So you can kind of see too how you can sort of skip this column once you're getting pretty comfortable with it. So you can kind of just go and answer the question here. So if 203 is greater than 128, just put your 1 straight in, but this can be helpful just as a sort of check while you're getting used to doing this. So we'll do question 3 now. I'll just get rid of all of these. All right. So our last one is 186. So again, start up here with 186. Is 186 greater than 128? Yes, it is. So we put a 1 in there. 186 minus 128 will give us 58. So is 58 greater than or equal to 64? No. Is it greater than or equal to 32? Yes, it is. So we put a 1 there. Then we do 58 minus 32 to give us 26. 26 is greater than or equal to 16. So yes, and a 1. 26 minus 16 gives us 10. Is 10 greater than or equal to 8? Sure is. So we get a 1 there as well. 10 minus 8 is 2. Is 2 greater than or equal to 4? Nope. So we get a 0 there. Bring the 2 down. Is 2 greater than or equal to 2? Yes, it is. So that's a 1. 2 minus 2 equals 0. Is 0 greater than or equal to 1? No. So we finish off with a 0. So the answer in this case is going to be equal to 1, 0, 1, 1, 1, 0, 1, 0. So that's our subtraction method of converting binary to decimal. Now, the other method for doing this is the remainder method, and that's what the next question is all about. So the remainder method, I'll go through it, but pretty much we're going to do those exact same 3 numbers so that you can kind of see that we get the same answer using the remainder method. So let's share the whiteboard again. So I'll clear all of this. So the remainder method is a little bit easier to remember, I think, because there's no table involved. So what we do is we repeatedly divide by the base. So A was 171, and we're wanting to convert that to binary. So at the moment, we don't know what it is. So the way that we do it is we divide that by 2, because binary is base 2. And then we write out our answer as the number and the remainder. So in this case, we've got 85 remainder 1. Then we take the 85 and we divide that by 2. And we end up with 42 remainder 1. Then we take the 42, divide it by 2. We end up with 21 remainder 1. Oh, sorry, remainder 0 that time. Getting ahead of myself. 21 divided by 2 will give us 10 remainder 1. 10 divided by 2 will give us 5 remainder 0. 5 divided by 2 gives us 2 remainder 1. And 2 divided by 2 gives us 1 remainder 0. And then lastly, we have 1 divided by 2, which gives us 0 remainder 1. So it ends when this is 0. So when the answer is 0 and there's some remainder is when it ends. Now the trick here is we actually don't read bottom to top. Sorry, we actually don't read top to bottom. We do read bottom to top. So we read this way and we fill out our answer using that. So our answer here is going to be 1 0 1 0 1 0 1 1. And if you have a look back to your notes from the previous question, you'll see that that's the same as we had for the subtraction method. So I'm just going to divide this board here and do the next one. So the next number was 203. So again, we divide by the base, which in this case is 2 because we're working with binary, and we end up with 101 remainder 1. Take our 101 down, divide it by 2, and we end up with 50 remainder 1. 50 divided by 2 gives us 25 remainder 0. 25 divided by 2 gives us 12 remainder 1. 12 divided by 2 gives us 6 remainder 0. 6 divided by 2 gives us 3 remainder 0. Then we have 3 divided by 2, which gives us 1 remainder 1. And lastly, we have 1 divided by 2, which gives us 0 remainder 1. So again, we can kind of read in this direction, and we end up with 1 1 0 0 1 0 1 1, which again, same answer that we got for the subtraction method. So I'll clear this now and do the last one. So the last one is 186. So again, just start the process of dividing by the base. So 186 divided by 2 gives us 93 remainder 0. 93 divided by 2 is equal to 46 remainder 1. 46 divided by 2 gives us 23 remainder 1. 23 divided by 2 gives us 11 remainder 1. And then we have 11 divided by 2 to give us 5 remainder 1. 5 divided by 2 gives us 2 remainder 1. Oh, actually, I messed that one up. That should have been a 0. 2 divided by 2 is equal to 1 remainder 0. And then lastly, 1 divided by 2 gives us 0 remainder 1. So yeah, I made a mistake up here. 46 divided by 2 shouldn't have had a remainder. But other than that, I think that those were all fine. So again, we just read from bottom to top off those remainders, and we get 1 0 1 1 1 0 1 0. And if we have a look at our subtraction method, we'll see that we had the same result there as well. So that is converting to binary. Next up, I have some questions on other bases. So binary is base 2. In exercise 4 and 5, we're going to look at things that are other bases, so base 5, 4, 9, various others in exercise 5. So converting other base n numbers to decimal actually follows the same process as a binary conversion, except we tend to write it out just as math. So you can do it as a table if you want with the place values and everything else, but I'll show you the way to do it with just multiplication. So let's share the whiteboard again. Clear all of this. So exercise 4, the first question was to convert 242 with a base of 5 to decimal. So again, you could do it as a little table with like place values and everything else, but you can just go 2 times 5 to the 2 plus 4 times 5 to the 1 plus 2 times 5 to the 0. So just to give you a little bit of intuition where all the stuff's coming from, let's pick a different color. So this here is going here. The 4 is that 4, and the 2 here is that 2. So we've kind of split those up into their place values. And then the powers, they kind of go up from right to left. So this is kind of the 1's place. So that's sort of 5 to the 0. You start from 0, then 1, then 2. And when you think about binary, it's actually working the same way. So this is a little bit of a detour, but let's say we had the binary number 111. We could convert that to decimal by doing 2 times 2 to the 1. Sorry, 1 times 2 to the 1. 1 times 2 squared plus 1 times 2 to the 1 plus 1 times 2 to the 0. So again, we've got those kind of ascending powers. So 0, 1, 2. The base is here because binary is base 2. And then these numbers come from these numbers. So the 3 different places of that number are here, here, and here. And then you would calculate the result as 1 times 4 plus 1 times 2 plus 1 times 1, which gives us 4 plus 2 plus 1, which gives us 7. So binary is actually doing the exact same thing. I just like the table mode for binary because it sort of steps it out very, very clearly, and you can reuse the table for multiple calculations. You could come up with a similar table for other bases though. So back to the actual task at hand, let's start to solve this. So we have 2 times 25 plus 4 times 5 plus 2 times 5, which gives us, 2 times 1, 5 to the 0 is 1. 50 plus 20 plus 2, which gives us 72 with a base of 10. Next question was to convert 2311 with a base of 4. Make that 4 a bit smaller so that it's clear it's the base, to base 10. So again, we can go 2 times 4. This time it'll be cubed because we have 4 numbers. So the highest power is like the number of numbers minus 1. Then we have plus 3 times 4 squared plus 1 times 4 to the 1 plus 1 times 4 to the 0. So then we'll end up with 2 times 4 cubed is 64. No, hang on. Yeah, 64. Yep. Plus 3 times 16 plus 1 times 4 plus 1 times 1. So we have 128 plus 48 plus 4 plus 1, which will give us 181 base 10. All right. Hopefully this is making sense and we're seeing a pattern. The last question then was 876 with a base of 9. So again, we take our first number and it's going to be 9 to the power of 2 this time because the number of numbers is 3, subtract 1 to give 2, plus 7 times 9 to the 1, plus 6 times 9 to the 0. So then we're going to have 8 times 81 plus 7 times 9 plus 6 times 1. So that's going to give us 648 plus 63 plus 6. And that gives us 717 with a base of 10. So that's converting any base number to decimal. The next question looks at how we can go the other way. So in these questions, we're going to look at going from a decimal number to a base of choosing. So let's have a look at the math for that. And this one's actually just remainder method. It works the same way as remainder method for binary, except we use a different denominator because we've got a different base. So let's bring up the whiteboard and clear it all. So exercise 5, question A was to convert 85 with a base of 10 to something in base 5. So convert to base 5. So we start off our remainder method the exact same way. Oh, actually, we're converting 86. Sorry, the background noise was my vacuum starting up. 86 with a base of 10 was the question. Sorry, I read it wrong off my sheet. So we start by dividing that number by the base, which in this case is going to be 5. And that's going to give us 17 remainder 1. And then we have 17 divided by 5 to give us 3 remainder 2. Then we have 3 divided by 5 to give us 0 remainder 3. And we have 0 in this place, so that's where we end. And again, we read bottom to top to give us 3, 2, 1 with a base of 5. So again, we just read off the remainders to generate our number. Cool, so then the next one was 304. Converting that to base 7. So again, we start off with our original number and we divide it by the base. And that's going to give us 43 remainder 3. 43 divided 7 is going to give us 6 remainder 1. And then 6 divided by 7 is going to give us 0 remainder 6. 0 there, so that's where we end. Read up, and we get 6, 1, 3 with a base of 7. And lastly, we had 65. So we're converting this one to base 3. So again, we start with our original number. We divide it by the base we want to get 21 remainder 2. 21 divided 3 is going to be 7 remainder 0. 7 divided 3 is going to be equal to 2 remainder 1. And 2 divided by 3 is going to be 0 remainder 2. 0 there, so that's where we stop. Read up, and we get 2102 with a base of 3. So again, just the same sort of process, divide by the base and keep track of the remainders and then read the remainders bottom to top to get the final answer. Cool, so that's kind of our base N exploration complete. Let's have a bit of a look again at our next questions. So next question is going to be on octal. So we've got some questions of converting to octal and some questions converting from octal to binary numbers. So let's have a look at how to do this. Let's bring up a whiteboard. Cool. So the first question is this number 1001 1002. That's 1001 with a base of 2. So that's a binary number. And we want to convert that to octal. Now in octal, we basically are looking for triplets. And each triplet gets converted to decimal. We put them all together for binary. So hopefully that'll make more sense as I work through this. But the first thing we need to deal with is the fact that we can't divide this into triplets. There's 8 numbers here. You can't divide 8 by 3. So what we can do is we can add a padding 0 out the front, which does absolutely nothing. So 0, 1, 0, 0, 1, 1, 0, 0, 1. So exactly the same number here with a 0 out front. So then we can kind of divide these up into 3. So we have 3 3s. And for each of these numbers, we kind of convert them to decimal. So 0, 1, 0 is going to be equal to 2 because we've got the 1, 2, 4 place. 1, 2, 4, 1, 2, 4. So the only bit that's on for this first triplet is the 2 place. So that's going to become a 2. If we have a look here, the bits that are on are 2 and 1. So 2 plus 1 is going to give us 3. And here, the only bit that's on is the 1 bit, so that's going to be 1. So the answer is going to be 2, 3, 1 with a base of 8. So you sort of divide it up into triplets, and then you find the decimal for each triplet, shove them all together, and add an 8. So that's how you convert to octal. You have to treat it as triplets. All right, so back the other way is a similar process. So we've got 127 with a base of 8 wanting to be converted back to binary. So we can do that as triplets. So if we want to represent 1 as a triplet, so again, for our triplets, we're going to have 4, 2, 1 as our possible places. So if we want to represent 1, we only want to turn on the 1 bit. So that's going to be 0, 0, 1. Then for 2, we need to work out the triplet for 2. So to create 2, we only switch on the 2 bit. So 0, 1, 0. And then for 7, to create 7, we're going to need to switch on all the bits, 4, 2, 1, because 4 plus 2 gives 6, plus 1 gives 7. So you can do these as proper binary conversions too. So if this is kind of a bit too confusing, you can just use the standard methods for converting. So you could, turn this into a table, or do something like, if you had 0, 1, 0, you could go 0 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 1 plus 0 times 2 to the 0. And that would give you 0 plus 2 plus 0 to give 2. So you could do that for this one here, if that's too confusing, just to jump to. And similarly, you can, for going back the other way, use the remainder method to calculate what your triplet would be. So you could do like 1 divided by 2 is equal to 0 remainder 1. And then that's going to be your only bit. So you can add some sort of padding zeros that way. But yeah, I mean, for these triplets, you can just sort of jump to it if you can familiarize yourself with that. Hopefully that's reasonably clear. So this actually asks for an 8-bit number, so we would drop the 0 at the start to give 8 bits, because that is the same number. The 0 doesn't make a difference. Cool. Next up, we have converting 253 with a base of 8 to decimal. Now, this is just going to be a standard conversion. So because it's base 8, octal is just base 8, you can just do 2 times 8 squared plus 5 times 8 to the 1 plus 3 times 8 to the 0. So this is the same math we were using in the question 2 questions ago, I think it was. Yep, exercise 4. We're just using base 8. Octal is just base 8. So we have 2 times, that's going to be 64, plus 5 times 8, plus 3 times 1, to give us 128 plus 40 plus 3, which is going to give us 171 with a base of 10. Cool. So that's our octal calculations. Yeah, any questions about those, feel free to pop them in the chat. I realize breaking it up into these triplets might be a little bit confusing, and working out what the triplets are. I think familiarizing yourself with this kind of little pattern is probably the quickest way to do these. But if that's too hard, you can kind of do the long way around of remainder method for decimal to binary, or the standard multiplication method for binary to decimal. Cool, let's have a look at our next question. Our next question is on hexadecimal. So hexadecimal is base 16, and it uses the numbers 0 through 9, as well as the letters A through F. So I'll write that up as a little table in a second, and then we're going to do some of these conversions from different forms to another. So let's have a look at what hex includes. So hex has the numbers 0, 1, 2, 3, 4, 5, 6, 7. Probably should have written these a little bit more compact, because they're not going to fit otherwise. 0, 1, 2, 3, 4. Okay, so the first 9 numbers are exactly the same. They're represented by their actual number. Once we get to 9, we switch to letters. So A, B, C, D, E, F. So that's the hex system. So this side is like our decimal, and this side is like our hex representation. So when we have the number A 1010, 0101, 1000, and 0111. Again, we kind of are doing a similar thing to Octal. Here we're splitting it up into sets of 4. So I'll grab my red and I'll just sort of make that really clear. So we're looking at each set of 4. So again, we've kind of got our 4 decimal places in this case of 1, 2, 4, and 8. So in this first one, only the 8 and the 2 bit are switched on. So that gives 10. In this second set of 4, we've got the 4 and the 1 bit switched on to give 1. So again, 1, 2, hang on, what did I do at the bottom there? We've got the 4 and the 1 bit switched on to give 5. I think I'm just reading ahead of my actual mouse. So again, we've got the 1, 2, 4, 8 bit there. In this one, we've only got the 8 bit switched on. And in this one, we've got the 4, 2, and 1 bit switched on. So 4 plus 2 plus 1 gives 7. So effectively, we've got a number of 10, 5, 8, 7. However, 10 from our hex table is represented by A. So A, 5, 8, 7. So the final answer is going to be, you can write it in a few different ways, but the common way is the 0x, A, F, 8, 7. So this just denotes that it's in hex now. Cool, so that's from binary to hex. To go back the other way, so we get our 0 times 8AF was the question. So to go back the other way, we kind of just do the inverse. So we can have a look at our table and kind of convert this to some numbers first. So we've basically got 8, 10, 15 here. So we need to work out which bits to switch on for each one. So we're going to have sort of our first set of 4. And again, we can kind of write out the places that we're working with. So 8, 4, 2, 1. If we want to create 8, then we need to only switch on the 8 bit. So 1, 0, 0, 0 would be our 8. To create 10, we're going to want to switch on the 8 and the 2 and leave the others off. So 1, 0, 1, 0. To create 15, switch on 8, switch on 4, switch on 2, switch on 1. It's the biggest number we can represent with 4 bits. So 1, 1, 1, 1. So again, the way to look at this is that sort of we've split it into chunks, and each chunk is either 1 hex number or 4-bit binary number. Hopefully that's reasonably clear. Again, you can do it the long way with remainder methods and stuff like that if that's going to help you out. And our last one asks us to convert this hex number, DC, to decimal. So the easiest way to do this is to remember that this is actually a base 16 number. So if we kind of write out what these numbers mean, so D means 13, C means 12. And each of these is, so this is in base 16. So what we can do is we can do 13, which is our D, times 16 to the 1, plus 12, which is our C, times 16 to the 0. So this is the same multiplication math that we've seen in all of the previous ones. So here we end up with 13 times 16 plus 12 times 1, and that's going to give us 220. So again, we've kind of used the the highest power here is the number of numbers, so 2 minus 1. So it's the same method we've used for the base n, the octal, same method, just you have to use, it's a little bit of a trick here to actually convert these to numbers first. I can probably show a slightly longer one to see if that will help a little bit too. So let's just, let's clear some space down the bottom and I'll go through a slightly longer one. So let's say I asked you to do 0 times, let's go 2a 3. So 2 is just 2, a is 10, and b is 3. Oh, sorry, that's 3, so 3 is 3. So then we have 2 times 16 to the 2, because this time we have 3 numbers, 3 minus 1 is 2. And then we have 10 times 16 to the 1, so 10 being our a, and then 3 times 16 to the 0. So this one's definitely going to require me to use a calculator. Give me a second. 16 times 16 times 2. That's going to give us 512 there. Oop. Plus 160 plus 3. So that's going to be 672 plus 3, which is going to give us 675. Hopefully I've done all that math right, but the main part is that this section here is correct and everything after that is just doing your math. Yeah, so it's the same as all of our other base n's, except we're using base 16 this time, and we have to be careful with our letters that we convert them to the correct number when we're doing sort of the math for those. Hopefully that's reasonably clear. Moving on now to our next exercise, which is signed magnitude. So in signed magnitude, we're using a single bit to represent whether a number is positive or negative. So let's have a bit of a look at how this works. It's not a very commonly used system because it has a lot of issues when it comes to doing math with these types of numbers, but I'll show you how it works. So the first question within exercise 8 is to convert negative 2310 to a signed magnitude number. So the first step is to work out what 23 is in binary. So let's do remainder method. 23 divided by 2 gives us 11 remainder 1. Then we have 11 divided by 2, which is 5 remainder 1. 5 divided by 2 gives us 2 remainder 1. 2 divided by 2 gives us 1 remainder 0. And 0 divided by 1 gives us 0 divided by 2 gives us, jumping ahead of myself. Sorry, 1 divided by 2 gives us 0 remainder 1. So we've actually only got 5 bits here. So to turn it into a 6-bit number, we just need to add some to turn it into an 8-bit number, we need to add some zeros out the front. So 0, 0, 0, 1, 0, 1, 1, 1. So that's a standard binary number for positive 23. To turn it into negative, all we do is replace the first bit with a 1. So the final answer is 1, 0, 0, 1, 0, 1, 1, 1 in a signed magnitude system. So the next question was to convert this number, 1, 0, 1, 0, 0, 1, 0, 1, to a decimal number. So again, because we're in a signed magnitude system now, these bits are the actual number, and this first bit is the sign. So that sign bit being 1 means that it's going to be a negative number. And then we need to work out which bits are switched on. So let's go through our place values again. So our place values are 1, 2, 4, 8, 16, 32, and 64. So the ones that are switched on are 32, 4, and 1. So we have negative 37 with a base of 10. So first bit is the sign, and then we add up all of the other ones that are switched on. So lastly, we have 0, 1, 0, 0, 1, 1, 1, 0. So again, first bit is the sign. The rest is the number. So straight away we can see this is going to be a positive number, and then we can have a look at which other bits are switched on. So again, our place values 1, 2, 3, 4, 5, 6. Oh, what am I doing? 1, 2, 4, 8, 16, 32, and 64. Sorry, I'm getting a bit ahead of myself with numbers today. I'm trying to talk and write at the same time. It's not really working out for me. Cool. So we go through and we see which ones are switched on. So we've got positive this time, 64 plus 8 plus 4 plus 2 are the place values that have a 1. And that's going to give us 78. So positive number that time, even though it's a sign magnitude system, we can still have both positive and negative numbers. It all depends on that first bit. So that's hopefully a little bit easier than octal and hex was. Next up, we have XSN. So XSN is a system that sort of shifts a number in order to represent it as a binary number. So XS 100 means that we have a shift of 100. We'll see what that means in a minute. 128 is a shift of 128, 64 is a shift of 64. So we're going to look at going both from decimal to binary in these systems and vice versa. So let's have a look at how this works. All right, so our first question is to convert -19 with a base of 10, so decimal -19, to an 8-bit XS 100 number. So step 1 is to apply a shift. So when we're going from decimal to binary, we shift by plus 100 because we've got an XS 100 system. So that gives us 81. And then we convert 81 to binary. So we go 81 divide 2, which gives us 40 remainder 1. 40 divided 2 gives us 20 remainder 0. 20 divided by 2 gives us 10 remainder 0. 10 divided by 2 gives us 5 remainder 0. 5 divided 2 gives us 2 remainder 1. 2 divided by 2 gives us 1 remainder 0. And 1 divided by 2 gives us 0 remainder 1. So then reading from top to bottom, we actually only have a 7-bit number there. So 1, 0, 1, 0, 0, 0, 1. To make it 8-bit, we just add a 0 out the front. And that's the answer. So -19, 10 is equal to that in XS 100. So the shift, and then just business as usual. All right, so then back the other way is pretty much the same thing. So if we've got a binary number, so in this case 0, 1, 1, 0, 0, 0, 1, 0, and this is XS 128. Step 1 is just to convert this to decimal. So again, we can write down our place values, 1, 2, 4, 8, 16, 32, 64, and 128. And we can add up all the ones that are switched on. So 64's on, 32's on, and 2's on. So that's going to give us 98. However, this is still in XS 128, so shift by 128. This time we have to go in the opposite direction, so we need to subtract 128 because we're going from binary to decimal. So it's 98 minus 128, which gives us -30, base 10. So that shift is really the only extra trick to this. Other than that, it's just business as usual with binary and decimal numbers. The last question was converting 0, 1, 0, 0, 1, 1, 1, 0, which was in XS 64, I think. Yep, XS 64. So again, we can have a look at our place values. I'm going to write them in again just so that we're really throwing this in. So 1, 2, 4, 8, 16, 32, 64, 128. Have a look at which ones are switched on. So we've got, oh, hang on, I wrote down the same number, didn't I? Yeah, I've written down the wrong number. Hang on. Must have been looking at an earlier exercise. So this should have been 1, 0, 1, 0, 1, 0, 1, 0. So have a look at the bits that are on. 128's on, 32's on, 8's on, and 2's on. So anything with a 1 is on. Add those up to get 170. And then we apply our shift. So again, we're going from binary to decimal, so we subtract the shift, and that gives us 106. So again, with both sign, magnitude, and excess n, whatever the n might be, you can represent both positive and negative numbers. Sign magnitude has its limitations because you basically lose a bit for a sign. Excess 64, excess 100, they can have some mathematical issues, but they kind of allow you to shift it so that a certain point is 0, and that can be a pretty handy way to represent stuff. So our final exercise is on 2's complement. So 2's complement is how most machines understand numbers now. It's a really handy system and it's not as limited mathematically. So we're going to have a look at how to convert numbers to 2's complement and vice versa. So there's a bit of a routine to this. So let's have a look at the steps involved. Let's bring up a whiteboard and clear all of those drawings. So first question is to convert -123 with a base of 10, so decimal number, to 2's complement. So for a negative number, there's 3 steps. First is to find the binary for the positive equivalent. So in this case, that's going to be 123. Then we want to invert all bits. And then we add 1. So step 1, let's start with step 1. So we just do remainder method as per usual. 123 divide 2 gives us 61 remainder 1. 61 divide 2 gives us 30 remainder 1. 30 divide 2 gives us 15 remainder 0. 15 divide 2 gives us 7 remainder 1. 7 divide 2 gives us 3 remainder 1. 3 divide 2 gives us 1 remainder 1. And 1 divide 2 gives us 0 remainder 1. So again, we can read from bottom to top. And again, we've only got a 7-bit number, 1, 1, 1, 1, 1, 0, 1, 1. So we can add a padding 0 at the front. So that's the result of step 1. In step 2, we flip all of those bits. So everywhere there's a 0, it becomes a 1. Everywhere there's a 1, it becomes a 0. So that's kind of the inverted number now. So then next up, we add 1. So pretty much because this is the 1 position, we make this a 1. So 1, 0, 0, 0, 0, 1, 0, 1. So that's now 1 number bigger than it was. So that is the 2's complement. That's the answer for A. Now, if we wanted to convert this back, what we do is we use a bit of a table. So all of the place values are pretty much the same as usual with one exception. So we have 1, 2, 4, 8, 16, 32, 64. This one here is -127. Oh, sorry, 128. So other than the last one, all of them are the same as usual. The last one is negative now, -128. So if I wanted to convert this number back, it would be -128 plus 4 plus 1, -123. So that's what we're about to do. The next questions are about converting back. So I'll clear this screen now. Hopefully that's reasonably clear. Next up, we had converting 1010 1001 to decimal. And again, this is in our 2's complement form. So again, helpful to put the place values in. So for 2's complement, it's the same as usual, except for the very last one is now a -128. So when we convert this, we have -128 plus 32 plus 8 plus 1. So all of the bits that are switched on are added up, and that gives us -87 with a base of 10. Last thing, we have question C is +105 with a base of 10. Now the steps are a little bit different for a positive number. There's only one step. Find the binary. So for a positive number, we just do the same thing we've always done, and we find our binary number. So we go through our remainder method. That's going to be 26 remainder 0, 6 divide 2, 13 divide 2, 6 remainder 1, that one. 6 divide 2 gives us 3 remainder 0. 3 divide 2 is 1 remainder 1. And lastly, 1 divide 2 is 0 remainder 1. So then we read off backwards. We get 1, 1, 0, 1, 0, 0, 1. That's only a 7-bit number, so to make it 8-bit, we add our padding 0 at the front. And that's it. That's the whole process for a positive number. And again, if you wanted to convert that back, so if you wanted to see what this number was using 2's complement, you can sort of write in your place values, 1, 2, 4, 8, 16, 32, 64, and negative 1, 2, 8. So then, oh, sorry, my Wacom just disconnected for a second, we're back. So then we can add up all the ones that are switched on. So then we end up with 64 plus 32 gives us 96, plus 9 gives us 105. So that's back to where we started. So pretty much with 2's complement, if the first number is a 1, it's going to be a negative number. Other than that, so if this is a, hang on, I'll grab my spotlight. If this here is a 1, then it's going to be a negative number. If this here is a 0, it's going to be a positive number. When you're going from decimal to binary in 2's complement, if it's a positive number, it's just normal binary conversion. If it's a negative number, you then have to do the invert and add 1 steps as well. So that's the only real trick there. So there's lots of different number systems for binary, and that's where things can get a bit confusing. You just need to be careful of having a look for which system you're being asked for, and then go from there. Hopefully this video has been helpful in terms of understanding how to do these conversions, because yeah, I realized that there's only sort of one example or so in the notes. So having both way conversions hopefully is going to be helpful when you're prepping for your test, for your quiz 2. If you have any questions, feel free to pop them in the chat, send an email, whatever works for you. Yeah, hopefully this is helpful, and I'll see you next week.